All right, so this is 9.3, Separable Differential Equations, Video 2. Really, this is just more examples. So if you feel like you have a good grasp on the other stuff, you don't necessarily need to look at these, although there's some things in here that I think might be helpful. There's also a bunch of old AP style questions at the end. Probably going to run through maybe one of them in this video. Chances are pretty good I'm not going to do any of the other ones as of right now. At some point in time, I may actually go ahead and do the other questions, and what I just said won't actually be true anymore. But at this point in time, I'm not planning to do more than just the first one. Okay, so let's see. If y prime is 7x squared over y cubed, and y of 3 equals 2, find the equation for y in terms of x. So we are trying to solve this separable differential equation. Again, we need to change the y prime into dy over dx first. So let's do that. 7x squared over y cubed. We're given the initial condition, so we'll be able to find c once we do this. So let's see. Let's multiply both sides by dx and y cubed, and that should do the trick. Y cubed dy equals 7x squared dx. Both are separated. Let's take the integral. Let's take the antiderivative. So antiderivative of the left will be 1/4 y to the 4th. On the right-hand side, that's going to be, it's the x cubed, so it'll be 7/3 x cubed plus c. We have now found our equation, so we can plug in the values to get c. So when x is 3, that'll be 3 cubed, which is 27. Y is 2, so that's going to be 2 to the 4th. 2, 4, 8, 16. That's 16 divided by 4, which will give us 4. So let's see, on the right-hand side, we get 7/3 times 27. Well, 27 divided by 3 is 9, times 7 is 63, plus c. So subtracting 63 on both sides, we should get that c equals -59. So let's plug that back in. We should have 1/4 y to the 4th equals 7/3 x cubed minus 59. Solving for y, we're going to multiply everything through by 4, which will give us 28/3 x cubed. 59 times 4, 60 times 4 is 240, subtracting 4, 236. Don't worry, I do not expect everybody to be able to do things in their head that fast, but if you can, wonderful. Just try not to make mistakes. And then we have to take the 4th root. It is an even root, so it will be a plus or minus. The 4th root of the entire right-hand side definitely cannot be simplified any further. So that's it. All right, moving on. More examples, number 2. dy over dx, they gave that to us already, equals 5x squared y. Initial conditions, find the equation for y in terms of x. So let's see, we can multiply the dx over and divide the y over. So we should get 1 over y dy equals 5x squared dx. This one does not look very challenging as of right now. Let's see what happens. We can take the integral. So let's see, we get the natural log of the absolute value of y. On the right-hand side, this will be 5/3 x cubed plus c. We have a way to find c. X is 0. That's going to make the right-hand side just c. The left-hand side, y is 6, so we get the natural log of 6. That's not very nice. So let's see, if we plug everything back in, we get the natural log of the absolute value of y equals 5/3 x cubed plus the natural log of 6. And then solving for y, we need to exponentiate, get the y out of that natural log. So that will leave us with y equals the exponential of e to the 5/3 x cubed plus natural log of 6. We can use that property that we did in video 1 to separate to e to the 5/3 x cubed times e to the natural log of 6. And make that look more like a cube. And since the e to the natural log, again, are composite functions, we're just going to end up with the argument. So that is just 6. So we should end up with y equals 6e to the 5/3 x cubed. That is our antiderivative. All right. It's a good practice to get into. If this was an AP class and not a college class, I would tell you don't even worry about simplifying because it's possible to lose points. However, this is a college class, so we definitely need to work on our algebraic skills and simplify to the best of our ability. Moving on to number 3. Oh, this one definitely looks more challenging. dy over dx equals 1 over y plus x squared y, and initial condition is given. You might look at that and think, well, there's no way I can separate that, but be careful because you can. If you factor a y out of the denominator, hopefully some of you saw to do that already, I would have y and then 1 plus x squared left over. Now these things can be separated. I can multiply the y to the left and multiply the dx to the right. So we should get y dy equals 1 over 1 plus x squared dx. We can now integrate, take antiderivatives. So the left-hand side should just be 1/2 y squared. The right-hand side, hopefully you'll remember your derivatives because this one is a special one. This is not something you can do a u substitution on. There's no extra x's to get rid of. So you have to remember that 1 over 1 plus x squared is the derivative of the inverse or arctangent of x. So the antiderivative here is arctangent or inverse tangent of x plus c. Okay, then we need to actually find c. So let's plug the x in for, let's plug the 0 in for x. So inverse tangent of 0 is 0. You have to know that tangent of 0 is 0 to know that the inverse tangent of 0 also works out to be 0. And then on the left-hand side, plugging a 2 in, 2 squared is 4, divided by 2 is 2. So ultimately, we get that c is 2. So now let's go ahead and plug that back in. 1/2 y squared equals inverse tangent of x plus 2. Solving for y, we'll multiply everything through by 2. Y squared equals 2 inverse tangent of x plus 4. And then take the square root. Once again, it is a square root, so we do the plus or minus of the square root of 2 inverse tangent of x plus 4. All right, one more of these types of examples, then we'll do the AP problem, and that'll finish up our video. All right, the separation looks pretty straightforward here. We can multiply through by dx and y squared on both sides. Got an initial condition which we'll use. So let's do that. We've got y squared dy equals e to the x dx. We can now take antiderivatives, so we'll integrate. And hopefully everybody understands that when I say take antiderivatives and integrate, the antiderivative is a process that you use to help solve integrals. Integrals themselves are not antiderivatives. Those are not the same thing. So please do not confuse what I am saying with being that they are synonymous with each other. Just the process is going to be the same from this point in order to get backwards and take the antiderivatives. All right, so this is going to be 1/3 y cubed. And antiderivative e to the x is just e to the x plus c. Initial conditions, x is 0. Remember that plugging in 0 into x here is e to the 0. That's 1. And on the left-hand side, y is 1, so that just gives us 1/3. So subtracting 1, we get that c is negative 2/3. Plug that back in, we get 1/3 y cubed equals e to the x minus 2/3. Multiply everything through by 3. Y cubed equals 3e to the x minus 2. And then we'll take the cube root. This is an odd root, so we do not need a plus or minus. Actually, it would be wrong to do so. That is our answer. All right, so again, that was just a few more standard examples. I do want to run through this one AP style question that we have on the next page. Again, there are multiple here. I am only going to do this one just because I think it's an interesting case to see. I don't remember what year this came from, but if you wanted to, you could. I'm sure you could look this up somehow. You could start typing them in. You could do that for the rest of them as well if you wanted to practice and/or see how to do them. So consider the differential equation that's given, where x cannot be 0. That should be obvious because you can't divide by 0. We want to sketch the slope field of the differential equation on the axis at the indicated points. We're to assume in this case that these points are 1 unit apart. So we basically just need to, let's see, we've got 8 points to plot. We need to figure out what's going on at all 8 of those points and sketch the slope field. The biggest thing is to, when you sketch a slope field, because these are relatively imprecise, we should pretty much know that a 0 slope is horizontal and that a 45-degree or slope of 1 should be at 45 degrees, excuse me. Everything else should kind of be relative to that because the slope of 2 is not easy to graph. Slope of 1/2, 1/4, it should all be relative to each other. So that's the easiest way to do it. Worst case scenario, you just label the slope at each point. All right, so let's see. At the point 1, 0. Okay, that's this guy right here. At the point 1, 0. If I plug in 1 for x and 0 for y, we would get 1 over 1. So that is a slope of 1. Again, about a 45-degree angle. Anything else I'll have to keep relative to that. At the point 2, 0. So that's going to be when x is 2, y is 0. So that's going to be 1/2. So that should be a less steep slope. And hopefully you can see that I kept it relative. It's less steep. Let's go to the point 1, 1. If I plug in 1 for x and y, I'm going to get 2 over 1. So that should be a 2. So that should be a more steep slope. That might have been too steep. So that should be more steep. And then if I go to the point 1, -1, so now x is 1 and y is -1. Y is -1. That makes the numerator 0. So 0 over whatever, as long as it's not 0, is going to give us a 0 or horizontal slope. As a matter of fact, we go to the left-hand side on the denominator, not the denominator, on the bottom left. That's also where y is -1, so that's also going to be a horizontal slope. Let's see, at -1, 0, so that's going to be 0 on, excuse me, plugging in a 0 for y is going to give me 1 on top and -1 on the bottom. That should be a -1 slope, -45-degree angle. And then let's see, at -2, 0, that's going to be a -1/2. So that's going to be less. Why is that not working? There we go. Less steep. And then at -1, 1, that's going to be a -2 slope, more steep in the negative direction. And you can kind of see how they're all relative to each other. All right, and there's your slope field. And the bottom part says, find the particular solution, y equals f of x, to the differential equation, given the initial condition f of -1 equals 1. So again, we have a way to find c. So let's go ahead and do that. So dy over dx was equal to 1 plus y over x. All right, this looks like we can separate, multiply the dx over, and we're going to have to divide by 1 plus y. So we should get 1 over 1 plus y dy equals still 1 over x dx, because the x didn't move out of the denominator there. Okay, we can now integrate, so we can take antiderivatives on both sides. All right, so the antiderivative of 1 over 1 plus y, remember if that was 1 over 1 plus y squared, that would be an inverse tangent. This is linear in the denominator. It's 1 over 1 plus y, so again, it's just a natural log. Absolute value of 1 plus y. And the right side, 1 over x, is the natural log absolute value of x plus c. All right, we have a way now to find our c value. We can plug in 1 and negative 1. If I plug in 1 for x, that's going to give me 0, so 0 plus c. If I plug in, excuse me, negative 1 got plugged in for x, but still it's the absolute value of negative 1, which is 1. Natural log of 1 is 0. If I plug in 1 for y, I'm going to get the natural log of 2. So c is the natural log of 2. Let's go ahead and plug all that back in. 1, oops, 1 over. Natural log absolute value of 1 plus y equals natural log absolute value of x plus natural log of 2. All right, so this one's an interesting case where every single piece here is a natural log. I'm still going to need to exponentiate because I've got to get that y out of the argument. So we're going to exponentiate both sides. We're going to use the property that we used before. So this is going to be 1 plus y. And on the right-hand side, this is going to be a little bit different because both of these two things are natural logs. The right-hand side is actually going to stay in its absolute value when I take the exponentiation here. So that's going to be e to the natural log of absolute value of x, but because both sides were natural logs, I got to keep one of them in its absolute value. So that's going to be the absolute value of x still. And then by that separation property, I've also got e to the natural log of 2, so that'll be times 2. So really what this gives us is 1 plus y equals 2 absolute value of x, and then to solve for y, we'll subtract 1 on both sides. So we get y equals 2 absolute value of x minus 1. Again, this only comes up when you've got natural logs of absolute values on both sides of the equation that you need to keep one of the absolute values. Now let me show you why this works. So this equation that we got here is an absolute value equation. And if you come back up here to our slope field and you look at it, while I'm going to erase all this stuff, you can see that each one of these things is an absolute value equation. Okay, those are all, now they should all be hitting right here. Those are all equations of absolute value. So this is the correct equation. We've got absolute value equations for all of these. Now here's the important part. The initial condition, where is it? There it is, was given to us as f of negative 1 equals 1. So that means when I took the negative 1, x is negative 1, and it gives us positive 1, it was really this point right here that we were using. So without the absolute value, we would actually have had to create a negative equation on the bottom. But the absolute value on the equation allows us to use the entire thing. Again, there will be certain ones of these where using certain parts of the antiderivative that you get down here, that you get down here at the bottom, like maybe you'll take a square root or something like that and you have to do the plus or minus, but because of the initial condition, you can only include either the plus or the minus depending on what the initial condition is. Otherwise, you would not actually have a function. So in this case, this one is just fine though. It does actually create that absolute value equation. All right, I think that's just about it. Again, the rest of these I will leave to you should you choose to look them up or not. At some point, maybe I will create a video for the other ones, but for right now, that is all.